Hello and welcome to the continuing videos for the linear algebra series. So in this video we're going to talk about transposes, although probably you've already seen a video introducing what transposes are. So the main part of this is going to be inverses, but we're also going to see some properties about both of them. So technically I'll stick transpose in the title. But the main part of this video is to talk about inverses. And this video is about what inverses are. So I'm sure will be other videos talking about methods for computing them and this and that. So this is about what inverses are, what's their definition, what do they mean, and how can we use them to a point. And then there will be other videos because it's a pretty big concept, so don't want to do it all in one video, about actual methods of computation. So here's what an inverse is. So in a previous video, we talked about what an identity matrix is. And so if we're talking about an actual number, we want to start talking about division. And we've talked about adding, subtracting, multiplying matrices, but we haven't talked about division. So let's think about what division is for real numbers. So this might seem like a weird way to look at it, but if you want to divide by 5, what we're really trying to do is undo multiplication. So 3 times what is equal to 12? That's the same thing as 12 divided by 3. Hopefully not any news or anything surprising here. Is that division is just trying to undo multiplication. So thinking about division can also be thought as multiplication as long as you multiply by the correct thing. For example, 12 divided by 3 can also be thought of as 12 multiplied by 1/3. Now, we've not seen fractions with matrices. We're not going to see fractions with matrices, but we want to come up with the next best thing. And this is why the notation kind of is the way it is we want to come up with the next best thing. How can we undo multiplication? And that's what an inverse is how can we undo multiplication? How can we come up with the equivalent to doing 1/3? And that's what an inverse is. It's coming up with the equivalent of doing 1/3. So in other words, B is an inverse of A if A times B is equal to 1. So again, feel free to pause the video and remind yourself what's the equivalent of being 1 in the matrix world. Because I'm thirsty and need a drink. That would be the identity. So B is an inverse of A if A times B is equal to the identity. So again, this will be something in concepts that'll be explored a little bit more in class in terms of a full picture of this. But for example, the inverse of 1, 2, 1, 3, an inverse, I forgot one thing. It has to work in both directions. So BA is equal to I. So for example, an inverse of 1, 2, 1, 3 would be 3, -2, -1, 1. And the reasoning for this would be since 1, 2, 1, 3, if we actually multiplied them, 1 times 3 is 3, 2 times -1 is -2, so that's 1. 1 times -2 plus 2 is 0. 1 times 3 and 3 times -1 is 0. 1 times -2, 3 times 1 is 1. But we also know that matrix multiplication is not commutative. So just because it multiplied on one side doesn't necessarily mean that it does it on the other. And so we'd have to check the other side we would get an identity that way. So this is what an inverse is. So a couple questions we want to be able to explore both in this video and going forward would be how to find an inverse. That's obviously important. Is there more than one inverse? We found one here, but I've never said that it was the only one. Is it possible to have more than one? Does every matrix have an inverse? Now, there's one matrix that should be pretty clearly the answer is no. Obviously, the zero matrix multiplied by anything, if it's defined at all, would be the zero matrix. And so that's kind of a boring example of something that doesn't have an inverse. But are there not non-zero matrices that don't have an inverse? These are all questions that we're going to want to explore. So let's start to answer some of those questions. Some of them will get answered in class. But just some facts about the inverses. The first thing is, one, we only have inverses of square matrices. In fact, that tends to be baked right into the definition. And the reason it's baked right into the definition is because if it's a non-square matrix, then AB and BA, even if they both exist, they wouldn't be the same size if it was a non-squared matrix. So when we're talking about matrices, we're talking about square matrices. I'll even put that in there. Let A be square. Because technically that's part of our definition. If A is a square matrix, we need that to be the case. If it's not square, then even if AB and BA are both defined, they're not the same size, and hence saying they're both equal to I doesn't even make any sense. The second fact that we have is if an inverse exists, it is unique. If an inverse exists, and that's a big if, but if an inverse exists, then it is unique. And we write A inverse. So that's our notation for the inverse of a matrix. It is unique. We're not going to prove that. You might talk about that proof in class. But if an inverse exists, it is unique. And for example, in order to prove that, that would say if B and C are both inverses, feel free to pause the video and ask yourself, what would you need to show? If B and C are both inverses, what would you need to show? Hope you had a chance to think about that. In other words, if A and B are both inverses, then B would be equal to C. So let's take a minute to think about why that would be. So this is actually just using a bunch of properties that we would already have. So let's start off with B. So B would be the same thing as B times I. Anything times the inverse, again, assuming the sizes all match up. These are all square matrices of the same size, so this would be defined. If C is an inverse, then what is I equal to? Because C is an inverse, what is I equal to? So again, feel free to pause the video and ask yourself that. If C is an inverse, what does I have to equal? Well, I has to be equal to two things. I has to be equal to both A times C and C times A. It's equal to both of them. That's what it meant for C to be an inverse. We're just going to use the first one. And then we're going to use a property that we would have seen in a previous video that allows us to move brackets around. Specifically, the associative property. Now remember, with matrix multiplication, we can't change the order. So we've got to make sure we're doing this carefully. We're not going to change the order of the matrix multiplication. We're just going to change the brackets. But since B times B is also an inverse, B times A is I, and B is equal to C. So if, again, big if, we made an assumption here that B and C were both inverses, that inverses existed at all. So if an inverse exists, there's only one. So that's our first big fact when it comes to this. Fact number 3. Fact number 3 is not all non-zero square matrices have inverses. The zero matrix obviously doesn't. Multiply that by anything, you get 0. But even non-zero square matrices some of them don't have inverses either. So that's going to be something we're going to see in other videos, is how to find the inverse if it exists, and how to tell when it doesn't. How to tell when a matrix doesn't have an inverse. And fortunately, for 2x2 matrices only, again, this is something else that you might want to think about, probably something that'll get discussed more in class. The answer is pretty complete and not too hard to remember. So if A is equal to the matrix A, B, C, D, then A inverse exists if and only if AD minus BC is equal to 0. And we're going to extend this concept in probably a little bit later videos in terms of what do you do if it's not a 2x2? What's an equivalent condition to this? But for 2x2s, it's fairly straightforward. And A inverse is 1 divided by AD minus BC, D negative B negative CA. And I'll leave it to you to give that one a try and to see why that in fact is true. In fact, we saw the example above with that one example that we did to show that an inverse is. So try it with this and see, as long as we're not dividing by 0, hence the condition we just talked about, as long as we're not dividing by 0, that if we multiplied by both sides, we see that in both directions, it's going to be equal to the identity. So these are some inverse properties. Of course, this leads to more questions like, what if it's not a 2x2? How do we handle that? For a more general idea as to how to find inverses, and we'll see that in future videos. All right, so a couple more properties, and this is where some of the inverse stuff comes into it, or transpose stuff comes into it. Let's just talk about some properties. And I'm not going to prove all of these together. We'll talk about them, maybe reason them out a little bit. But maybe just ask yourself, assuming that A and B are invertible, being invertible means you can find an inverse. What do you think the inverse of A times B inverse would be? Again, invertible and the same size. They're not the same size, the same square matrix, that multiplication would not be defined. So if you had a chance, maybe pause the video, think about it, and it might seem like it should be this. But ask yourself, all right, how could we prove that? So if this was true, that would say AB times A inverse B inverse would have to be equal to I. But is that necessarily true? I mean, if we think of inverses as canceling off multiplication, we might say, oh wait, B and B inverse, that gives you the identity. A and A inverse, that gives you the identity. But we have to be a bit careful here. If we have these together, are we really multiplying B times B inverse? And the answer to that is no. And the reasoning is multiplication is not commutative. It's not B times B inverse. It's B times A inverse that's getting multiplied first. You can't just do the multiplication whatever order you want. So what we have here would be a whole lot better if the B inverse was right there. And in fact, that's exactly what the real property would be. It's not A inverse times B inverse, it's B inverse times A inverse, in order to have the B right next to the B inverse. Again, you can feel free to think about how the full proof of that would go. In fact, the same thing is true for the transpose. So for both inverse and transpose, there is a property that says you can take the inverse of the product or the transpose of the product, but the order switches. It's not A transpose B transpose, it's the other way around. Unless the original matrices were commutative to begin with, but usually that's not the case. And in fact, there's some more properties where it comes to transposes that are fairly obvious. A transpose transpose. Let you feel free to pause the video if you want to, although this one you might be able to reason out. If taking the transpose once turns rows into columns, taking the transpose again would turn the columns back to the rows. So that's just equal to A. None of these are particularly surprising. The only one that's really surprising is perhaps changing the order. He's right here. All right, so those last four are some transpose properties. But let's ask ourselves, could we do the same thing with the inverse? Let's get some green here. What about A inverse inverse, assuming that it was invertible and this thing actually exists? So let's think about that. That's A times A inverse is equal to I. So the inverse of A is A inverse. What's the inverse of A inverse? Well, that takes you back to A. In the same way that 1 over 1 over 3 was just equal to 3, if we talked about inverses of real numbers. So perhaps that's not too surprising. Perhaps a more interesting question, and feel free to pause the video and think about this. What would be the inverse of K times A? All right. So, again, maybe you had a chance to think this. Hopefully you paused the video if you didn't. Again, we want to think of this as being an equivalent thing to division. So the inverse of K times A is going to be something times A inverse. But remember, we want to cancel off the A and cancel off the K. How do we cancel off the constant K? That would be 1 over K Of course, in that case, k cannot be 0. There's actually one more fancy property that I'll let you think about. We can actually rearrange the inverse and the transpose as well, which is why it made sense to put them together in a video. So we have all these things, but there's one property that seems to be missing. One property that seems to be missing. Yeah, there wasn't one for addition. And that's for good reason. This is not equal to A inverse plus B inverse. You could change the order if you want. It's still not going to be true. In fact, if A and B are invertible, you can add them together and get something that's not invertible. So this might not even be defined. And there's one final one. If we took A to the n. So what A to the n means, n being a positive integer, means pretty much what you would think it means. A cubed would be A times A times A. So hopefully that notation is not overly surprising. We're not going to see any fractional exponents, no A to the 1/3. We don't have a cube root. Not to say they don't exist, but a little bit beyond that. Inverse is the same thing as A inverse to the power of n. And in fact, often we'll shorthand that as just A to the negative n. So A to the negative n doesn't mean we are putting it in a denominator, because there is no fractions, but it means we would take the inverse multiplied by itself n times. All right, so these are our properties. Obviously, the big thing we want to get to is how to find the inverse of any particular matrix. But if we have these properties, we can work with them once we know how to find them. All right, that's it for this video. See you in the next one.